So we started talking about Rao, or the so-called information inequality. And the idea is that this is an application of the Cauchy-Schwarz inequality, and it gives you a bound on the variance of any unbiased estimator. So we already have seen that in cases where you have a complete sufficient statistic, there is the UMVU that you potentially can compute, and potentially the variance of that can be computed. And if you can do that, then that would be a lower bound on the variance of any unbiased estimators. But this is a much easier approach. And as we'll see, the bound that it gives is much easier to calculate, much easier to calculate, doesn't require the existence of completeness. Whether it's tight, in some cases, it matches the UMVU bound. In some cases, it's not as good, but gives you a lower bound in any case. So the plan is to use this version of the Cauchy-Schwarz, so variance equality. So on the lower bound, the variance of an unbiased estimator. If I pick it the proper psi here, I can potentially calculate the right and the idea that we explored last time in this HCR is if I take the likelihood to be, the psi to be the likelihood. So I want to have, I want to use this inequality. I'm going to drop the theta for simplicity. This is bigger than covariance of delta and psi squared divided by the variance of psi. So what we do is, okay, I have to put back theta here. We take psi to be this quantity. This quantity, which is the likelihood ratio minus 1. So I'm going to take psi to be L theta and H minus 1. So the idea is that I want to, I take two parameters like theta and theta plus H, and fix these two, and then I can define a psi like that. And then this potentially gives me a lower bound, as we'll see. The only reason that we have to be a little bit careful is the fact that this ratio makes sense, and this is this absolute continuity assumption. So if p theta plus h is absolutely continuous with to p theta, then there is a well-defined likelihood ratio. So here I actually go over that a little bit, and we're going to be very brief here, so we're not going to worry too much about the measure theory context, but very quickly, this condition is equivalent to that. So whenever, suppose they have both densities, so our assumption is that these have densities with respect to some underlying measure, with respect to mu, then this condition translates to whenever this density is 0, it's like that. In other words, the support of this guy is contained in the support of that guy. And so when I form this likelihood ratio, I don't have to worry about the case where this is 0 and this is non-zero. Oh, sorry. Yeah, so this is 0 and it's not. So that would be infinite and we have a problem. But whenever this is 0, this is going to be 0. So oftentimes it doesn't matter what this value is, so you can arbitrarily define it that way. And whenever this is non-zero and this is 0, it's fine. So the reason this condition is made is to make this likelihood ratio relevant. From a theoretical perspective, this is also that there are other variables to that, but we're not going to worry about that. So the main use of this formula, or the likelihood ratio, is this change of measure idea or formula. And the idea is that I can integrate. So the likelihood ratio allows me to translate expectations from one measure to another. Okay, that's the main use. And the idea is very simple. So like it's spelled out here, but if I want to maybe do it a little bit more less compactly. So you had expectation of, let's say I want to calculate the expectation of delta x under, let's look at this the other way, under theta plus h. So what this means is that x is distributed by p theta plus h. Okay, so we're assuming that x has the distribution. Remember this notation. This means x is distributed like this. So we are under this distribution. And I want to somehow relate this to some expectation under another distribution state. Okay, and the point is this can be done. And it turns out that this is going to be that times that likelihood ratio, which I defined above. Okay. L theta h of x. So another way of doing it is like theta plus h is modeling, we just call it something else. So call it like theta prime. So this allows me to, roughly speaking, translate from p theta prime to p theta. Sounds good. So the way that this works is you'd write it just as delta x p theta plus hx dx. So it's enough. So this is, or okay, being mu if you want to be precise. So I can add this condition over the set of all x's such that p theta plus h x is bigger than 0. Because where it's 0, we don't need to worry about the integral, it's 0. And then this translates into, it's enough to take it where p theta of x is bigger than 0, the same thing. Because wherever this is positive, this is positive. So there are other, so it's just like this condition is p theta of x 0 implies p theta plus h is 0. The contrapositive is that p theta plus h being positive implies p theta of x being positive. So so I can do this. And then on this, under this condition, this is well defined. So I'm going to write this as p theta plus hx divided by p theta x times p theta x dx. So that's the likelihood ratio. Okay, and you can now see that this is this whole thing is now a random variable. And I'm integrating this density. So this is really just the expectation under theta, because we're taking the integral in there of this quantity L theta h x. Okay. So that's what we have here. Good. So likelihood ratio translates expectations. Okay, so we're going to use it a couple of times. So let's see how we can use it here. So for example, if I want to calculate, let's do this here. Copy, cut. So if I want to do that, I need to calculate, for example, expectation of psi of x under theta, right? Or under, let's say, theta plus h. Okay, let's not worry about that. So let's, I think, do this. This is going to be expectation of L theta hx minus 1. And then you compare, if I plug in delta equal 1, right, expectation of L theta h is this when delta is 1. So I'll look at the other side. So this is going to be just the expectation of L theta h x under theta plus h. Sorry, still this is not the theta plus h 1. So this is 1 minus 1 is 0. Okay. So that formula allows me to calculate the expectation of this rather straight in a straightforward fashion. What else do I need? I need expectation of theta delta x times psi of x. Right, so this is going to give me expectation of delta x L theta h x minus expectation of delta x. So we're assuming, so if you remember the setup, you're assuming that we're looking at unbiased estimators. So delta x is assumption. Delta x is unbiased for, let's say, some parameter g theta. So this quantity would be, what would this be? Or g theta, yes, it's unbiased for g theta. Right. This one would be from that formula, this quantity, which is g theta plus h, right? Because they're unbiased. Biasness means the expectation of this under any parameter is the desired quantity. So this I have calculated g theta plus h. And so if I now plug that in, so this is going to be, because psi is 0, the covariance is just the expectation of delta x psi x, which we calculated here. So you get g theta plus h minus g theta squared. And the variance is just expectation of theta psi x squared, which is just what it is. So expectation of L theta h x minus, no, yeah, that's squared. Sounds good. Okay, and if you look at this side does not depend on delta anymore. It depends on theta and h, but doesn't matter. So this is called Hammerstein-Chapman-Robbins inequality. It gives you a lower bound. Okay, and the theta is assumed to be fixed. H is up to me. I can vary h. I get different lower bounds. And whenever you have a lower bound, you try to optimize it, try to find the tightest. So you want to push it as high as possible. And it turns out to push it as high as possible, you need to let h go to 0. In that case, both the numerator and denominator go to 0, but it's hard to see what happens. But so let's say, is this clear so far? So this is that theorem. So if I divide by h squared, both the numerator and denominator, I can this holds for any h, so I can let, as long as, let's say, this condition holds. Let's say for all h small enough this holds, then I can let h go to 0. So as h goes to 0, good things happen. So what would happen to the numerator? I get g theta plus h minus g theta divided by h squared. H goes to 0. The derivative goes to the derivative, right? A theta squared. Denominator is interesting, so let's do it here. So I get the expectation of p theta plus h divided by p theta of x minus 1 squared. We want to let limit of this as h goes to 0. Here's the tricky part. If I can interchange the limit and expectation, which is, as you may know, in measure theory, you have to worry about it. But a good chunk of measure theory, or like Pascal measure theories, try to justify this under various conditions. It's possible to exchange the limit and expectation. So if I do that, then what is this? So this is right. Anyone knows what this would be? This. Add a page here. So what is this limit? We rearrange it. We get p theta plus h, x minus p theta x. Divided by p theta of x. So I'm gonna do, oh, there's an h, okay. So there's, so we have 1 over h squared here. Because we divide it here, okay. So there's 1 over h squared. So I get this over h squared, the whole thing squared, right? So it's really limit goes inside, I get limit, which goes to 0, p theta plus h x, p theta of x, divided by h, and then divided by p theta of x, the whole thing squared. Okay. So what do we get? We get another derivative. So I'm going to write it as partial with respect to theta of p theta x, and then divided by p theta of x, right? Which is really the partial derivative of log p theta of x. Okay, so the end result here is that this is expectation of partial derivative of log p theta of x squared, yes. Great. So putting back together, I get the lower bound that I want, which is variance of g prime theta squared divided by this is going to be x squared. Okay. So this is the Kramer-Rao bound. This quantity is called the Fisher information matrix. No, not the matrix, but this just Fisher information. As you can see, it's a positive quantity and it measures the information of the model. Why it measures information, you can see from here that if this is large, then this variance is still much smaller. Okay, so you can potentially write down the variance being smaller. If it is small, the information is high, then this is higher, so the variance of the unbiased estimator is higher, like the best unbiased estimator. And so it's like 1 over this measures like how well the variance behaves. So it has notion of information built into it. Okay. So this other quantity, the quantity that's inside, this quantity has a name. Anyone knows what this is called? Score function. Is that it? What is it? Entropy. No. I heard the score. Score function, yes. The statistician would call this the score function. And as you can see, it's like related to the derivative of the likelihood ratio, but it's like a derivative. So this is this is the likelihood of the function of theta when we look at it. Remember, this is the likelihood. This is the log likelihood, and so the derivative of the log likelihood, which is the derivative of this function. So theta is called the score function. Okay, so and if you follow through the argument that we did, I'll talk about this again. If you okay, so we talk about this later. This turned out to have a like zero mean. The mean of this is 0, so this is really also the covariance. Sorry, the variance of the score function. Okay, we'll talk about it. So this is Kramer-Rauwald. And we could be happy with this, yes.
Oh, sorry.
Yeah, we could be happy with this if you're okay with this argument, or we could be unhappy and try to make it a little more formal, which I often do, but let's see how unhappy you are with this argument. But go ahead, yes.
I had a question about our earlier step. When we're integrating against the likelihood ratio function to perform the change in variables.
Yes.
Or, yeah, I was wondering, or the change in measure, I mean.
Yeah.
We like the two distributions that we use like P of theta and P of theta plus H.
Yes.
Like in like a general sense, we don't have to just like, it doesn't have to be theta plus H. It can be any distribution as long as like the likelihood ratio.
Yes, exactly. Yes. So yeah, more generally, good point. So I could have, let's say, like a distribution Q, which is absolutely continuous with respect to P. Okay. And if you want to measure theoretically, so this is written like this. They don't even have to be, I don't even have to talk about the density with respect to underlying. So there is this likelihood ratio, which is the Radon-Nikodym derivative. And if you think about it, okay, it might be like too abstract, but if they have densities, let's say this has density Qx, with respect to some underlying measure, this has density Px, this is really Qx divided by Px. Okay, so this is really a function. Okay, and then if I want to like take the integral or the expectation, let's say under Q of some g of x, then this is the expectation under P of gx, that quantity. And write it as dq dpx. So you can just substitute it like q of capital X divided by P of x. So that's the general formula. Okay. And so this, we can apply that. That's precisely that. So I should probably have done it like this, but because we're in that context. I did it with that. The only reason why that particular thing is useful when theta basically is a linear parameter, so in a linear space, then we can let h go to 0 and then this nice thing happens. But this idea is more general. Okay. Any other questions? Okay. Yeah.
Variance of
Psi, yeah. So variance of psi. Yeah. Why is that? Yes. Once the expectation is 0, this equality holds. Right. So we use it both for the numerator and the denominator. Okay. Sounds good. Okay, so if you're happy with this argument, then we can move on. I have like a more formal statement, and I'm gonna briefly go over it because it's also more general. So we did it for a single like real value parameter, as you can see. I have been so this edge I'm dividing by edge. So implicitly, I have mentioned implicitly something that's invariant or like a scalar. But you can also state a result for a multivariate parameter. The main issue is how to make sense of the variance. Okay, so if for example, the theta is in, let's say let me see actually what I did here. Yeah, okay, so let me state it here. So this is the formal statement in multi-dimensional. So let P be an element of the family. The density is having some support, so this is going to be what we're using. We're hopefully going to get these 7 terms out. So P dominant means they have density respect to some other language, and the densities all have to support the S. And then I have some open parameters, so it's omega and RD. So that's where theta lives. And so okay, so now theta itself is d-dimensional, but the parameter that I want to estimate is like some scalar function or thing. Okay, that we can do. Okay, so even more general version. So there's an even more general version where this could be M. I'll talk about that later. But in that case, you have to figure out what we mean by the variance. Yes, but in this case, at least in this fairly simple case, any estimator of this would be real value. That has a relevance if you talk about that. So suppose I have delta, which is unbiased for this. There are a bunch of other conditions here. So for example, G has to be differentiable, and I'm going to write the gradient and leave a dot. So these are so this G is a multivariate function, right? So G goes from R D to R. And so there is a gradient. I'm gonna write it like that. Okay, so this is really partial derivatives, just to remind you. So it's a d-dimensional vector, partial derivatives of the function evaluated theta. That's gonna be my notation. And I'll also write it as G dot for simplicity. Okay, so implicitly evaluated at theta, I'm not putting theta. So it's too much compactness. Like a physics notation, or Newton's sort of derivative, which didn't catch up, except in physics. We're going to be using physics notation. That's the gradient. And then we have I'm going to use this notation for the log, for the likelihood, or the log likelihood, sorry, the log likelihood as a function of theta. I'm going to do dots. So for example, well, this is going to have a gradient, right? So this is going to have a gradient, which I'm going to represent with a dot as well. So it's a gradient of this, which would be, in this case, it's a little bit tricky to write, but that's just gradient of this function. And I'm going to write it as L theta dot X and sometimes drop X, so it will be that. So this quantity is the score function. Score function, and it's really a random variable because of dependence on X, but also it's like a function as a function of theta. Okay, like the likelihood. So a random function. So this is my notation. And you're going to assume that this guy, the score function exists for all X to be almost all X, but let's say for some to be all X in S and all theta in omega. So the likelihood is differentiable. And G is also differentiable. So these derivatives make sense. And this is the technical condition. We're going to assume that whenever I integrate some function against d theta or this S, so this is going to end up being a function of theta. I can take the derivative. Basically, partial derivative I call it. And I can move this inside the this is the assumption that I'm going to make. And it's really exactly what I need. Okay. Implicitly assume it. And then under what condition this holds, we don't talk about that. Okay. So we're like under like regular enough. Let's say at least you need the support. You have to worry about this. Support depends on theta, and this is tricky, right? This is also variable theta derivatives. If the support is fixed, then at least they formally introduce. And this is making the assumption that this holds for it should at least hold for PC equal 1 and PC equal rather than we consider, but generally we will assume that for basically any PC which is sufficiently regular this holds. And so under these assumptions, any unbiased system, so that delta be any unbiased system with G theta will satisfy this lower bound. The variance will satisfy this lower bound. And so we can see this is like G theta, and this is the derivative. It's like G prime theta squared divided by pi, but now this is a vector and this is a matrix. So that efficient information is the matrix in this thing which where vector so it's quadratic form. So what is efficient information? Efficient information was like remember it was, in our previous notation it was, if I want to write it, so this would be expectation L dot theta X squared, right? So this is not a score function. In the multivariate case, so univariate or a scalar G theta, multivariate case, multivariate or scalar theta, G theta. So multivariate theta, I can't just square it because it's a vector. So instead you would get L theta X times L theta X dot transpose. So this is, let's say, a D by 1 vector. This is a 1 by D vector. So this product is a D by D matrix. And then I take the expectation, in this case, efficient information matrix. Right. Let's go back and see this is the definition. So I'm dropping X everywhere. So L theta dot and theta dot. Take the expectation. Okay, any question about the statement? So this is the key idea, and this is essentially, if you translate it to our setting, it's like a differential form of that change of variable formula. So let's rewrite it. I've written the assumption here. In this part, right, we can write it as, I'm going to divide, right? So this, you look at this, divide and multiply by p theta of x, right? So when I divide it by p theta of x, and then multiply by p theta of x, the first term would be the derivative of the mod. Right? So this partial derivative, I have p theta. Okay. And so, then this is really, you can see the expectation of this quantity against the data. So it's like expectation of the theta of this one, which is just, this is the derivative, right? So this is the score function, L dot theta of x. So I really have this, okay? And this side is really, this is just the expectation of QC, right? And the partial derivative. So what we have is, this identity is really partial derivative of expectation of QC is equal to okay, this is the gradient, so it's bad notation. So this is the ith coordinate, because this is a gradient, this is really the ith coordinate. So this is equal to expectation under theta of QC, and then the L dot, the ith coordinate. And if I write everything in a vector, this side would be the gradient, this side would just be gradient, so you get this expression. So this is the coordinate wise statement, this is the vector version. So the gradient of expectation in C is equal to expectation of PC. So this is performing the rule of the likelihood ratio, like infinitesimal likelihood ratio. Right, so before we had something like that, right? So that's the change of rail. So this is the differential form of that state. Okay, so that's the role that the score function plays. It's like how much, like how the expectations change in a very small change to it. One. Okay, so we, yeah. Right, so this is basically the ith coordinate of the gradient. So what this is saying is that the ith derivative of this, so this is like this gradient ith coordinate. Okay. How do you treat that? This index, so the derivative is there. So I'm just like, we write this assumption. This is the assumption, right? So we have the assumption. And then I multiply and divide by p theta. So that produces this expression. Right, so this is there. And I just noticed that this is the ith coordinate of this one. If it's too confusing, let's do this. This is just partial derivative. I'm just replacing it. Partial derivative with respect to log p theta of x. Okay, and so this would be that. This is x. Does that make sense? This is just this. So that's the function I'm integrating against the density. Right, so this whole thing is this. Okay. So let's write x, cx, and that. Okay, so this is just a rewrite. And then once you stack them, this side will be the gradient. This is scalar. So it's like this time the gradient, this is the gradient. Right. Another way of writing is just gradient. Expectation of QCX is equal to expectation of QCX gradient theta log p theta of x. Okay. You can see the representation if you want. much nicer than all the x's, gradient floating around. So. Sounds good. Okay, so we just like basically cheat it because we needed this, we just assumed this. To like push the complexity to the assumption. But once you have it, then what happens if I say t is equal to 1? So the other side is 0 because the gradient of a constant function is 0. So you get that the score function is really 0. Okay. And if I plug in delta, I get gradient of expectation of delta, right? Delta is unbiased for g theta, right? So you get expectation of delta. This is equal to the gradient of gt. Okay. But this is a little bit problematic because both sides are vectors. So I want to apply this Cauchy-Schwarz law where we're dealing with variances. So I can't take, for example, psi, remember psi was a scalar value. So they're going to use a trick, which is going to be very helpful. So what's the trick? So I want to use this identity variance of divided by variance of psi. So delta is a scalar value. But remember, psi was like magnitude ratio -1. Here, I want to use some sort of score function. The score function is multivariate. How do you deal with that? Change what? How do you change it to numeric? So what was that? Great, great, great. So that's the idea. So what we're going to do is we're going to look at a linear combination of score functions. So this is also like some psi. Okay, so I'm going to just take psi to be basically A transpose L dot theta for some A, which I can choose. So this is performing the linear combination. Was that like something that we've seen before, or is it something? Okay, so this is very interesting. Whenever you deal with a vector, and you need some sort of scalar out of it, so you make a scalar like this is going to be linear transformation. And then I have an extra parameter A to worry about later, but at least I made it into a scalar, just form a linear combination. So we can plug that in there. So once I have this, so A is just some fixed vector in Rd. Because the score function is 0, I mean, what is the expectation of this guy, psi? 0. It would be like transpose this linearity of expectation. That's why linear things are good. So the expectation is going to transpose 0, which is 0. So 0 mean, so this formula is still valid. So this is going to be expectation of delta psi, right? Because the covariance, the other term vanishes. And this is also going to be expectation of psi squared. So that's because of the 0 mean nature of psi. So let's calculate the numerator. So I need to calculate the expectation of delta psi squared, right? Which is really expectation of, oh, sorry, square is outside. This squared. delta psi. So that would be expectation of delta A transpose L dot. Right. What happens here? Yeah, so use linearity of expectation. So this is like a linear combination, like AI, I from 1 to D, L dot I, right? And the delta is, you can put it here, for example. So expectation moves. And if you think about it, it's like equivalent to A transpose expectation of delta L dot. And we have it here. So this expectation is here, right? That's the same thing. And I just replace it with gradient of G theta, which, by the way, I wrote it as, in our notation, it's just G dot to avoid G dot of theta. Okay, I have all the ingredients. So this is going to be A transpose G dot of theta squared. And then the denominator is expectation of psi, which is A transpose L dot squared. Okay. So that's good, because we have a lower bound. We have a parameter A, but this side doesn't depend on delta. So we found the lower bound. The only issue is that there is A, but I'm free to choose A. So if I'm free to choose A, what would you do? Take the derivative with respect to A. So like a little bit more generally, it's okay, but set it equal to 1. I can set it equal to anything I want. But you want to do what? You want to have a best lower bound. What will be the best lower bound? Like max. Okay, so yeah. So the idea that this is a function, they auto maximize it. Just do that. So whenever you have a lower bound and you have it like a, sorry, let me just write it down, and then you're gonna do the maximization in your homework problem. Okay, max over A in RD, A transpose G dot theta squared. So at this point, the problem leaves the land of statistics and enters the realm of optimization. So there's no statistics involved. So you're not going to worry about that in this course. So this is now an optimization problem. So you go to an optimization class and ask people to do it. Why it's an optimization problem? Because it's like this. So max, I actually have it somewhere here probably. Right, so it's something like this. Max, or if you want a soup, like A transpose V, write it there. It's of the form max, you want A to be non-zero, right? Otherwise this doesn't make sense. In RD, A non-zero, A transpose V squared divided by, okay, we have to be a little bit more, I need to do a little bit more work here. And I'm going to say that this is equal to A transpose B A. But let's do that. I forgot to do that. So this can be simplified. There's this other trick that you can use to get to see the Fisher information before we do the optimization. So how can we simplify this? Anyone knows how to do the trick?
Like this, where does the transpose, how does the transpose and then?
Great. Yeah. So this is like whenever you have a square of this way, you write it twice, but flip it around. So this times itself but I'm gonna write it this way because it's a scalar, I can transpose it. Make it the same. So this is a very useful trick. So what happens now? Yes, yes. So pull the A's out, you get A transpose, expectation goes in L dot transpose, and you see our beloved Fisher information appears. Right. So now my optimization is of the form of this form, where V is G dot theta and V is I theta. Okay, and now this is like a proper optimization problem. We try to solve it. And the end result is that the solution of this optimization problem is V transpose V inverse V, which is one of your homework problems. Okay, so it gives me G dot theta, I theta inverse, and G dot theta. So there's a transpose here. So that's the Kramer-Alba. Okay. So the only trick is to use this. Oh, there are two tricks. So I gave three tricks. So first we assume this differential identity, which is effectively like differential form of the change of measure, and also like the idea of interchanging expectation and differentiation. The second trick is to deal with the multivariate nature. So we introduce this linear combination trick. And the last is this very common trick to make the differentiation come out. So at this point, this is deterministic matrix. And then this is a deterministic optimization problem, which is solved by basically by decomposing this. There is some hint. Okay. But we proved Fisher Kramer-Alba, and you can see naturally the Fisher information comes out. And moreover, because we proved that L theta dot under our assumptions is zero mean, this is also the covariance matrix of this side. If you remember what the covariance matrix is, the Fisher information is also, we also proved under our assumptions that I theta is really the covariance matrix of L dot. Because the covariance matrix is this term minus the expectation of L dot times the L dot. That's sort of that term is zero. So this the Fisher information is really the covariance matrix of that sort of. Because it's a covariance matrix, it's positive semi-definite. In the univariate case, it's positive, so it has the meaning of information. You don't have negative information, mostly or zero. Okay, so Fisher information matrix is positive semi-definite as a consequence. And in most cases, it's strictly positive definite, so it's inversion. Otherwise, you run into issues. But because it's positive semi-definite, and the inverse is also positive semi-definite. If you remember positive semi-definite, if this quantity is non-negative, because it's like V transpose positive semi-definite by definition is non-negative. So the lower one is also negative. So a lot of information can be gathered from this. Okay. So you have a positive. It wouldn't be useful if it was potentially negative because we know that the zero is a lower one. So this is in general, this is strictly positive definite. This is in general going to be hopefully non-negative. And it's like, it's always non-negative, hopefully it's gonna be strictly positive. The only way that's gonna be zero, let's say the derivative is it can be zero because we're assuming that this is there's no zero eigenvalues, so it's gonna be strictly positive on their assumptions, assuming that you can invert it. Okay. Questions? We prove this. Or this slide. So that's the result. We prove that the variance is lower bounded by this quantity.
So where did that 80 go?
So the A disappears at this stage. Once I maximize over A, there's no longer an A. So what I'm saying is this optimization problem solution exists. I haven't proven this, but you're gonna do it. Once you maximize over A, there's no longer.
Yeah, yeah.
Okay. So it's an interesting argument. It's not difficult, but there are a bunch of tricks that are used, which are helpful to remember how to deal with the multivariate sort of quantities. That's one way of dealing with this trick. And then the fact that once you have a lower bound with a free parameter, you want to maximize. Questions? Okay, some remarks. So the regularity assumptions for interchanging the integral derivative are key. And so with unbiasedness, under the assumptions, in the assumptions, you can also show that the integral represents other expressions, the negative of the second derivative. A second derivative is Hessian, so it's like the simple notation of this being the Hessian matrix. So you take the Hessian matrix of the likelihood, negative of it. So this has a lot of information in it. So the Hessian of a function is a measure of its curvature. So imagine if you have, and implicitly you can see that because it makes this positive, and you can see the negative over here. So the likelihood is curved this way. So it's like, for example, if I have like a function, let's say it's like theta squared, then this look like this, right? Let's say this is like alpha times that. And so the second derivative would be 2 alpha, right? You can see if alpha is, this is actually negative. Okay, let's say negative, a positive number times alpha. So this is going to be negative 2 alpha theta. So if alpha is large, right, what would happen? Right. There's no theta, right? So this has constant curvature everywhere, in a sense. We measure like, but as you can see, it's like if alpha is very small, what would it look like? It would be like flatter, right? So this is small alpha. This is larger alpha, right? So if alpha is large, then when you move a little bit, you just go very fast. So this alpha, second derivative measures the curvature. And so what it's saying is like basically negative on the curvature in this case, because it's curved negatively. So so negative over this positive. But this quantity measures the local curvature. And so this average curvature of the likelihood. And so what it's saying is that the average curvature determines the information. And that's really sort of true. In the interest of time, we're going to not talk about this stuff. I think you go to the lecture videos from the previous year. I have a description of why intuitively the curvature of the likelihood is related to the equilibrium. But it's a very nice idea that the geometric quantity is related to information. This is related to statistical information as we saw, and we see multiple times later, because it appears in the lower bound of the Kramer. So if this is high, you can potentially write the variance down, and this is the geometric quantity. It connects like information to geometry, and people like this idea. The information geometry, some like line of work in statistics, traditional classical, tries to understand sort of information of the statistical model via their geometry. To attainment, so there's attainment, whether the bound is attained, it is sort of related to being an exponential family, so. If I'm not wrong, so this came up in the previous one, so there's a statement that shows that it happens. You can only be an exponential family. I didn't under some conditions, so. The thing that means like, the minimum possible variance is the variance of U and V, whether that's symmetric, it's seems to be that. And then efficient information is not invariant under reparameterization. So if I reparameterize, efficient information changes. So if I have a different parameter, remember, for example, the exponential parameter, you have two interesting parameters, the canonical parameter and the mean parameter. So the efficient information changes depending on the parameter because of this basic definition, because it's the derivative, right? So you have the efficient information is the partial derivatives of this with respect to squared, right? So because of this, when I take the parameter, there's the Taylor differentiation. Verify. But the CRV is invariant. It's both efficient information changes and also the derivative G. The derivative G, so theta is now, if you want to derivative like that, and there's a change going on. And so this extra term comes out that translate between the two just vanishes from the, it cancels out from the numerator. No, so it's the argument in the maybe this is another instance. The recent problems that I forgot. But this is good because good news statistically, because you don't want a lower bound that changes as you reparameterize. And this is because the statistical nature of the problem is not going to change if you reparameterize. You can make the problem harder or easier. Very specific problem. And then efficient information is added in more independent something. So this is really something simple, but notation-wise, it's going to be tricky because, okay, so because we, like, and then it's a source of a lot of confusion later on. So oftentimes, so this, everything that we talked about is false for a general parametric family, but we often work with families that are derived from IID, like univariate case. So let's say I have, for example, let's say, for example, xi's are, can we do that? So this part is quite important, at least if you don't want to be confused. A simple idea, but important. So let's say I have x1 up to xn from the same distribution parametric, let's say density. I'm going to write 1 here to avoid confusion. So this is univariate density. And then the joint density, I'm going to drop the 1. So this is, if you want, is n, if you want, or let's do it like, for example, x1 to be not confusing. So this x is multivariate, x1 up to xn. So now, under this IID assumption, this is a special case of the models that we look at. So this can be written like that. Okay, I put the 1 there to avoid confusion. So this is really a univariate function. This is a multivariate function. And so once you do that, then if you take the log, you get log p theta of x is sum over I log p theta 1 of xi. Differentiate with respect to, let's say, theta j if you want. And you can see things go in. Oh, actually, it doesn't go in, right? So it's like a sum. And actually goes in, yes. It goes in. Is that true?
Yes.
Okay, so what do we get? We get p theta 1 I. Correct? Okay, so let's do it like univariate theta. right? This is univariate for simplicity. Right. Are we good? And then the second derivative. What happens if I do the second derivative? Same thing happens here. So now the Fisher information would be negative expectation of this partial derivative. Log p theta of x. Although we didn't show, but if you believe me, then you get summation I from 1 to n, negative expectation of p theta 1. It's I. Okay, and so this expectation is under the general model, but in this term, you just have to decide, and these are all IID. Okay, so these are all the same. And this is like the Fisher information of a single model. Okay. It's the base model. And so because you have some of them, you get n times I1 of theta. So the Fisher information of the joint model is n times the Fisher information of a single model. And this is very good because it says that IID sample just linearly increases information. Every sample just has like one of these Fisher information, which is very nice. Sounds good. If you don't have, this is like their dependence, where you know this is a Markov chain, so x1, x2 depends on x1 and so on. The rate of increase as you increase the number of samples might be slower than that. Okay, and maybe there is a homework problem, I forgot. That you construct a sequence, infinite sequence that has finite Fisher information. So this is when you go to infinity as the sample size grows, but you can have a dependent sequence that the information sort of dies down and eventually like the sum is like finite. Okay, so there's finite information within like the infinite sequence. This happens for dependent process, so you have to worry a little bit about that. Okay. Questions? Okay, so these are all the comments. And later on, this will come out. So we're going to, for example, talk about asymptotic variances. This distinction is going to be important. So let's remember that. Come back. So a couple of like final points. This whole thing can be generalized in the case we have multiple parameters. So if G goes from RD goes into Rm, then the issue is that unbiased estimators of G are going to be vector value. So there's no single variance, but we'll have a covariance matrix. It turns out that you can write a multivariate version of the figure out, but saying that the covariance matrix of delta is going to be lower bounded by this quantity, and this lower bound is in the sense of matrices. So what this means is that the difference of these two matrices is positive and negative. Okay, so this is a particular order among matrices. And so this you can easily prove by the same technique that we just learned. So instead of looking, so we looked at like A transpose times the score function. Here you're gonna look at A transpose times delta. So A transpose times delta will be unbiased for A transpose times G theta. Then you're gonna apply the Fingerel to this, and then this will hold for all A, and then we can make this into things. It's important. So this you can do as an exercise. So there's this Fisher information there, and this J here replaces the G, the gradient. So this is the code. So G has like multiple components, and theta has multiple terms. All the possible derivatives, if you collect them, it's called the Jacobian ring. So you get the Jacobian matrix, the Fisher information matrix, inverse and Jacobian transforms. So we're gonna not use that much, so maybe not yet, but worry about that. Let's do a simple example on this here. So this is the Gaussian family where sigma squared fixed, let's say it's one, so take that. If you look at the log's likelihood, this has this expansion, and because you want to take the derivatives of the theta, we collect everything that depends on theta and all the things that don't depend. The constants of this thing have to be like that. Take the first derivative, you get this result, and you can see if you take the expectation on both sides. Because the expectation, I'm sorry, theta is a 0, so you're actually verified at that point. And then the second derivative is just going to be negative numbers. So it's a quadratic function. So second derivative. So this is like a simple case that I have. Like, this is very similar to this figure that I showed. Okay, so that's the likelihood of the Gaussian. And so it has constant sort of temperature. It's simple. So you can see that the information is like that, and then derivative you think is 1. So the lower one is really 1 over I think. That then you need to take that. So I'm going to switch sequence over n. And you can easily remember that in this case, the sample mean has this variance. So the proof of the sample mean is your mu, and you generalize it. There's a simple way of proving. We didn't use any completeness, we just know the sample mean has its variance, and this analysis of this kind of feedback. So we prove that sample mean. Yeah, so it's really 1 over, so variance. This is 1 over, in this case, that's the Fermat-Rao boundary. Sounds good? Okay, there are a couple of more examples, which I'm going to go through next time, hopefully, and then we start a new topic. Sounds good? Okay, thank you guys.